My name is Victor Wakili, and this is my ECE 178 Embedded Systems project. For my project, I decided to take a text file from the SD card and display it using the VGA output of the DE2 115 board. So I'm going to talk about quickly about the background of the DE2 board, quarters and QSys, and how we use that in my project. Talk about some specific IP cores, then a quick project description with the block diagram, and then a software description that talks about the algorithms and the flowchart, and then I'll finish the demonstration with a demonstration. So quick background about the Altera FPGA DE2 115 board. It uses the Cyclone 4 processor, and it has several types of memory that can be used for the programs, as well as a bunch of other peripherals such as the 7-segment displays, the LEDs, both red and green, switches, and the push buttons. And some of the most important ones for this project is going to be the SD card slot. It is important it is formatted with FAT16 file type so that the SD card can locate the blocks of data correctly. And the VGA output, which has several IP cores associated with it, that must also be configured and synchronized correctly. So a little background about Quarters and QSys. Quarters was one of the main programs that I used when constructing the project. It is used to create hardware modules using HDL. I specifically used it because it includes QSys, and QSys is a system integration tool. And within QSys, I was able to build my custom system. I added all the IP cores that I needed and made a connection, generated the HDL, and then after that, I instantiated it within Quarters using Verilog, hardware description language. After the program was compiled, everything was okay, and I got done with the project. So one of the IP cores that was most important for me was the SD interface card IP core. And so I've got several buffers and registers here that are very important to learn how to use correctly. First one was the CMD register, which contains the address to be read from. You send the address of the block of data you want to read from or write to. The next one is the CMD, which is the register that we place the value of the command you want to perform. And in my case, it's 0x11. The next one is the RxTX, which is 512 bytes of data to be read. It is capable of being filled with data. Once the buffer is filled, the SD card will then transfer the data over to the board. And finally, we got the ASR register. It has several important bits that gives you information about the status of the SD cards and the operation. Bit 0 tells the last command is valid. Bit 1 tells if the SD card is present in the slot. Bit 3 tells the current state of the status is valid. So in terms of the project description, I wanted to take a text file from an SD card and insert it into the FPGA board, read it, and then display it via output using the VGA output controller into a computer monitor. In order to do this, I needed to create a custom Neo system using QSys. I had to use all the IP cores that was necessary. Some of the most important one was the SD card interface, the VGA controller, some timers, buffers, and translation signals. The VGA controller we run at 25 megahertz and the board runs at 50 megahertz, so I had to include some PLL in order to synchronize it to the buffer, where the character buffer and the pixel buffer, and those were used to display the text also clear the screen and the computer monitor. I used a program called HXD, which is the hex reader, in order to locate which file block the SD card block is. The data was on the SD card. After I knew which location the SD card was, we used that location to transfer the information from the SD card to the FPGA board. The data was processed and is prepared to be displayed using the VGA output, and finally I displayed the text file from the SD card to the monitor. So here I have a block diagram of the project, and on the right there is an output from the HXD program which shows exactly what sector of the SD card the text file is going to be located at. You can also see the actual format of the text file, which has a bunch of hex file used that represent the ASCII characters that will be displayed on the monitor. It's very easy to implement on the information on the SD card using this information. And as you can see on the left back to the block diagram, we take data from the SD card, which is then sent to the SD interface with all those registers and buffers I mentioned earlier. That data is sent to the Neos 2 processor, and then that's being run out of a laptop, which runs Altera monitor program, and then it's connected to the FPGA board using the DE2's USB blaster. Next, all the information is sent into the SDRAM, which contains all the buffers and timers that are important for synchronizing the VGA controller and the most important components. And then once everything is good to go, it goes to the VGA controller, which is finally displayed on the monitor. This is a description of the program that I used to make the project work. First, initialize the cursor position to say where the character is going to be displayed on the monitor. After that, we'll check to see if the SD card is inserted by constantly checking bit 1 in the ASR register. If no card was inserted, it would just keep looking, and after the SD card was found, we'll write the address block to the CMD argument register, and then I'll write the 0x11 to read, as I mentioned earlier, to the command argument register. After that, I'll check to see if the SD card is busy. Since it's flash memory, it takes a little longer than other memories. Then a brief delay will be used to allow the VGA to be configured correctly. I then sent a bunch of black pixels to the screen in order to make it all black, and after that I finally displayed the message from the SD card to the monitor. So I'm going to finish the project here with a little bit of a demonstration. As you can see, the laptop is running the Altera monitor program using the DA2 board from the USB blaster. And from the Altera monitor program, you see behind the laptop, you see the monitor at the back, and it kind of shows like a colored screen. In second here, when I press the run button from the Altera monitor program, you see the monitor from the back change from the garbled mess that it is to the black screen with the text at the back. And we can see the text matches the previous slides that had the location of the file in memory. In conclusion, I would say this one was pretty fun, challenging, definitely very challenging, educational because I learned a lot, and engaging. It took a little bit of time because I missed some classes, but getting the class notes from my friends and everything definitely helped, and I got a little bit of help from my friends, and appreciate that. That'll be it for this project. Thank you very much.